So we do an iterative SHA-1 operation. First, we take the first half of the pool, hash it using SHA-1. Then we update one cell at I. Then we take the second part of the pool, hash it again using SHA-1 tag, and I'll say in a minute what's SHA-1 tag, and use it to update two additional cells. That's in I-1 and I-2. Then we do again SHA-1 tag and take the output, and from SHA we get 20 bytes of output, and the authors were afraid that someone will find an attack for SHA-1, that by the way is coming this year, and they added another layer of folding. So they take the 20 bytes and they fold it. They take 10 and 10 and XOR them into the result. And that's the output. So a very, very complex structure for the extraction of output from the pool. And again, as you could see, there are a lot of extraction. One when we read bytes from the dev random or from the dev U random, and whenever there isn't enough entropy in the small pools, in the secondary and the U random, we get additional entropy from the primary pool. Also, they didn't take the SHA-1 as is, but in the second and the third time, they used SHA-1 tag with no reason. They just changed the IV, the initialization vector, just like that. It took us a while to find out, but I'm not sure why they did it. Okay, that's the extraction procedure. Mm-hmm. It's a good one. Good question. They just take the initial bits, the first 32 bits. You're right. The output of SHA-1 is 160 bits, and they take just the first 32 bits. Okay, so that's the extraction. And as you could see, it's a very, very complex structure. We have 3 different pools. We have entropy estimation. We have a collection asynchronously. We have addition using some complex generalization of linear feedback shift register. When you extract bytes, you do 3 SHA-1s, and when there isn't enough entropy, you extract from the first pool to the secondary with a feedback back, a very, very complex structure. Unfortunately, it's complex but not secure. First, I'm going to describe 3 attacks. Okay? The first one is theoretical, but it is very bad. I'm going to describe it in a minute. The theoretical result is very bad for the authors. The second is, and I guess that you could see it once you saw the description of the protocol, it is very easy to mount a denial of service attack. And I'm going to go into the details. And the third attack, as I mentioned, is a very practical one on a unique Linux distribution, OpenWRT. And you can guess, and in a few seconds, a few minutes, you'll see why. It's very easy to attack it. I'll give you a hint. It has to do with entropy or with the lack of entropy. Okay, so just the theoretical one first. As I mentioned, the entropy-based PRNGs, we want to have 3 properties: the backward security, forward security, and pseudo-randomness. We were able to mount an attack, again, mostly theoretical, on the Linux on its backward security, meaning my input is the state of the PRNG. I assume that you were able to break into a Linux machine, get the entire memory dump, and go away. Give me this memory dump. I have the entire state of the PRNG. And what you're going to see in the next slides, that I'm able to trace back past outputs of the PRNG. Yes? No. No. So the input of my attack is the state in stage N, and the output of my attack is the state in stage N-1, and of course also the output in state N-1. And I can run it for several times. Also, this attack is limited with the fact that I assume that during the attack there is no entropy addition during that time. Just to make sure that you see that it's not trivial, if you try a brute force attack, the number of operation is very large, that 2 in the power of 10^24. That's impractical. And that's the number is the size of the pool, of course. So if you just want to do some brute force, you need to guess the entire pool state. But we can do much better. Actually, if we have the state, let's look at the extraction process. What we do in the extraction process, at each stage, we update 3 words. As you could see earlier, we updated 3 words. The word at index I, I-1, and I-2. So these 3 were updated. So if I want to do a brute force, a simpler brute force, all I need to do is guess these 3 words. So I'm going down from 2 in the power of 10^24 to 2 in the power of 96. And that's, of course, much better. Again, as I said, it's mostly theoretic because 2 in the power of 96 isn't so practical today, but it's almost there. So that's very easy. And, of course, very easy also to understand it. And I can do it repeatedly. I can do it for one stage, for another stage, and I can go back and back. But there is some limitation. When we did it, we came into a problem. We call it the simulation problem, that we start with a single state and we trace back. The green ones are the true values that we found. But because we are doing a complex combinatorial operation, we find, in addition to the true exact value, we find also imaginary ones. That's the yellow at the bottom. And we were afraid in the beginning that this will escalate very fast, exponentially. And we will have, after 2 or 3 stages, some huge number that you would say, okay, that's impractical. I cannot use it. Actually, and I won't get into the details, we did the combinatorial analysis and also some measurements, and the growth isn't exponential. The growth is linear. So after 100 stages, you'll have at most 100 imaginary values, which is, in security, is great. Very, very, very good result. How do I know after 100 stages how to take apart the imaginary ones? I'll skip the math. How do I know to solve the imaginary ones? I'm using the upper protocol. What's the upper protocol? Depends on your users. But let me remind you, we are using random number generators for some security application like SSL. So take each one of the 100 that you got from me and try using it on your encryption. If you get clear text that makes sense, that's the right one. Then you broke the security protocol. So that's the way to use it. That's the way to use the simulation program. In some ways, in some cases, we were able even to mount a better attack than the 2 in the power of 96. In some cases, we were able to do it in 2 stages and break the 96 bits into 64 and 32, and then the attack becomes 2 in the power of 64. And that's, again, an advantage. And again, as I mentioned, that's a mainly theoretical result because first you need to break into a machine. Okay, that's sometimes practical. You need to get a dump of the memory, and then you need to compute 2 in the power of 64 or 2 in the power of 96, which is quite expensive. You probably won't use it. So that's mostly for the theoretical part of my talk. But as I mentioned in the beginning, when we are designing a security protocol or cryptography protocol, there is no reason that we'll have such flaws. And it's very easy to correct these, and I'll get back to it. Denial of service. Right now, there is no limitation on the using of dev random or dev urandom. So if I am a user on your machine, I can just open dev random and read. And of course, I'll finish all the entropy in the system, and your process, which may need just 4 bytes, may go to sleep forever. That's starvation in Unix, Linux. And that's very easy to implement, and there is no limitation on how many bits you can read. I can do it internally when I'm another process reading from dev random. I can do it internally when I'm another process reading from dev urandom, because both of them are using the same pool, the same main pool as I mentioned earlier. And I can do it even remotely, because some of the remote protocols are using random number generators from the system. One of them which we already mentioned is the TCP sequence numbers. But there are some more. For example, DNS. Again, SSL. So I can use all of them remotely to consume all your random bits, and you won't get any. That's starvation. And there is a very simple solution for that in operating systems, implementing a quota. And I hope that's one of our recommendations. And there are already discussions in the Linux kernel group of implementing quota for the random number generator. That's an easy way to handle such things. So that's denial of service attack. And as I mentioned,